So we're going to look at some linear plots today, and we're not going to fully look at our equations of lines yet. We're going to wait a unit. We're just going to slowly build into it. So today we're just looking at linear relationships. So we're just going to still deal with plots. You know, it's like a scatter plot. But now these plots, every time they're graphed, they should represent a line when connected. That's what we're mainly looking at. And hopefully we should notice that all of these plots, or these linear relationships that we have what we say a constant rate of change. And you'll see that as we go. So basically, it should change at the exact same rate every single time. So if I have a dot, it's going to go over some and up some, and it's going to have another dot. And it's going to go over that same amount and up that same amount and another dot. And it keeps going like that. So it kind of represents a linear, right? A line linear relationship. So that's what we're kind of looking for today. So something you'll see will be like this. It'll say list the terms of the y-coordinates shown on this graph, then write a recursive routine for the sequence. Well, when we get to the recursive routine, remember we're just saying where it starts and what is the rule. Remember recursion, you got to know where it starts and you got to know the rule. Well, let's just write all these points first of all. So let's see. What are my x's counting by? It looks like they're counting by ones. So I can tell by that 5 at the end. Same thing with my y's. These are counting by ones. So this first point right here would be what point? Well, did it go over in the x at all? No, it didn't move left or right. What about its y? It went up halfway up, so 0.5. What about the next dot? Let's see. So that's over 1 in the x direction, right? And then it went up just past 1, but not quite 2, right in the middle, so 1.5. Do I notice the pattern already? Hopefully we do. So my next point would be 2, right? Every time I go up 1 in the x, I go up how much in the y? Another 1. So this should be 2.5, I'm guessing. If I look over 2, up 2.5. Yep, so I should be able to finish this out now. So then I got 3, 3.5, and 4, 4.5. I just wrote them all out. You don't have to do that. But it says list the terms of the y-coordinates shown on this graph. So that's all I wanted to do was take a look at the y-coordinates. Well, that would be all these guys. So 0.5, 1.5, 2.5, 3.5, 4.5. So I'm going to write all those. 0.5, 1.5, 2.5, so on and so forth. So those are my y-coordinates right there. That's the first part. And then it says write a recursive routine for the sequence. Well, here's the sequence. I just wrote it. So recursive routine, where does it start? It starts at 0.5. And what is the rule? Well, we just talked about that, right? It goes up plus 1 each time. So I would say plus 1. Okay, so don't forget to write that recursive rule as well with that. All right, you're going to see some funky notation in your book today. But let's just talk about what it really means. It says plot the first 5 points by the recursive routine below. Well, this is just written in what you would do on a calculator, and more specifically a graphing calculator like a TI 83 or 84. But we're just going to pay attention by what it's doing. So remember, for a recursive routine, there's a start and there's a rule. Well, here's our start. That's our starting point. So I'm going to write that down here. That's the point 4, -1. So let's go ahead and graph that. 4, -1. That'd be about right there, 4, -1. Okay, and then let's look at what the rule says. This is kind of goofy, right? What is my rule stating? Well, it's stating take answer 1. What do you think answer 1 is? Yeah, this guy right here. That's our first answer, whereas answer 2 will be right here, the second one. Okay, so I'm going to take answer 1, and I'm going to add 1 to it. So that's all I do. I just add 1 onto that 4. So if I add 1 onto the 4, I should be at 5. And then I do the same thing for answer 2. I'm going to take answer 2, and I'm going to subtract 2 from it. So I'm at -1, and I'm going to minus 2. And that would put me at what? -3. So there's my next point. 5, -3. I'm going to plot that point. And the same thing should occur every single time. I should add 1 in the x direction, and I should subtract 2 in the y direction. So my next point would be 6, -5. So I'd be at 6, -5. And hopefully, you should be able to just tell that you're going right 1 and down 2 to get your next point. And it says how many? Plot the first 5 points, so I got to get 1 more. So right 1, down 2. There we go. And if I notice, these guys are making a linear relationship, right? So if I follow the same recursion rule by adding 1 in the x and subtracting 2 in the y, it has a linear relationship, right? If I were to connect these dots, it would make a straight line. So you don't have to draw that line in there, but just take a look at why it's making a straight line, because it has a constant rate of change, right? It's adding by 1 on the x, subtracting by 2 on the y. That's why we say it's a constant rate of change. Lastly, now let's use the actual situation here. It says a bicyclist 1 mile, which is 5,280 feet, away, pedals towards you at a rate of 600 feet per minute for 3 minutes. The bicyclist then pedals at a rate of 1,000 feet per minute for the next 5 minutes. Describe what you think the plot of time distance from you will look like. Well, describe. Okay. So what would that look like, you think? Well, let's actually graph it first, just so we can take a look and have some guesses on what it would look like. So B says graph the data using 1 minute intervals. So we can use a nice little L graph because it's all positives. We're not going into negative minutes or negative feet. And then what could I put for my labels? Where did my time go? Well, it tells us up here. We got the X always comes first, followed by the Y. X's should be time, and the Y should be distance. But what should we use, miles or feet? What do you think? Well, our rates are in feet per minute, right? So let's put that in feet. So this is the distance. So I should specify and say that we're using feet. Same thing with time. I should specify and say that we're using minutes. And I'm going to mark this off. 1 minute, 2, 3, 4, 5, 6, 7, 8. So I can count by ones there. That sounds good. And if I'm with feet, where should I start at? I'm starting at 5,280. So what should I count by, you think? Should I count by ones? No, that's way too small. Hundreds? Still too small. Thousands? Yeah, I'd say maybe 1,000 would work. So 1,000, 2,000, 3, 4, 5,000. So where would my first point be? Would it be up high, or would it be like right at the origin? Well, when 0 time has gone by, 0 minutes have gone by, how far is the bicyclist away? Yeah, 5,280 feet, a whole mile. So when no time has gone by, so I'm starting way up here, so I can put a dot right up top there. So this might actually help to make a table in this case. I like making tables whenever I'm going to graph. So X, Y. So there's my minutes, and the Y is my feet. So at 0 minutes, I'm 5,280 feet away. Well, in 1 minute, how far would I be? Well, it says for the first 3 minutes, we're going to go 600 feet per minute. We're going to get that much closer. So I have to subtract 600 from 5,280, which put me at 4,680. And that's going to happen for the first 3 minutes. So let's go ahead and do that for the first 3. So then I'd be at 4,080, and then I'd be at 3,480, right? So I subtract 600 each time. But then what happens? It says it's going 1,000 feet per minute for the next 5 minutes. So 4, 5, 6, 7, 8. There's the next 5 minutes. So 1,000 now. So 2,480, right? Because I'm subtracting 1,000, and then 1,480, and then 480. And then guess what? What's going to happen right here? We'll talk about that. Okay, so let's go graph all those points first of all. So I got 1, 4,680. And then I 2, 4,080. So it should kind of make a straight line right off the bat. Obviously, I did mine by hand, so it's not the greatest. So it should still make a straight line. 3,480. I'm just going to write that one so we can see 3,480. All right, now it's going to start jumping. 4 and 2,480. So that's like there. So that one dropped a little bit more. Then 5, 1,480. And then 6, 480. And then, well, it's going to be in negatives, but would I graph that? Should I graph the next one? No, we're not going to go in negative feet here. So let's think about this. Describe what you think the plot time distance will look like. Well, it looks like it's going to keep moving down, right? Because we started up at 5,280 for our distance. So our plots are going to keep moving down. And what happens after 3 minutes? after 3 minutes, the points will decrease faster, right? Because it went from 600 feet a minute to 1,000 feet a minute. So that's really all we can kind of tell. And then what about C? It says invent a question about the situation and use your graph to answer the question. Well, the bicyclist was 5,280 feet away. So you can maybe say like, how long will it take for the bicyclist to reach you? Right, because he's getting closer and closer and closer and closer to you. Well, what would I do? I would look at my graph and make an estimate. So at 6 minutes, he's just about to me. At 7 minutes, I know he's going to be past me. So it's like somewhere right in there. So I could say a little more than 6 minutes. So just by making a graph, I was able to tell at what point that bicyclist would reach me. Okay, so we're not going crazy with lines yet, but we're just looking at the relationship by making some plots.